Hello guys, so I am back with the normal equations now. So what we have done, let's revise a bit. We have done the following. So we have this data xi comma yi, and we did this model that yi follows what? Beta naught plus beta 1 xi plus epsilon I, where epsilon I follows are independent and follows some distribution with 0 and sigma square mean and variance correspondingly. And then what we have done, we have done we have seen that the corresponding loss function, right? We have defined the loss function L of theta hat, but theta hat is this beta naught, and not theta hat but theta curl. The set of vectors, set of parameters is summation of yi minus beta naught minus beta 1 xi whole square, right? And what we did next, we have to minimize loss function to get the theta hat, right? That is beta 1 hat, beta naught hat, and beta 1 hat. So we do argmin theta of L of theta. Okay, so this is the called theory of least squares, right? This is the basic idea of theory of least squares. So how do we use this to go to and like correspondingly estimate those theta hats? That is the aim of this video. That is done by something called normal equations. Okay, so what is the normal equation? Normal equation gives rise to the minimizing equations from this corresponding like least squares. Okay, so let's try to do it. So what we are trying to minimize, we are minimize L theta hat, which is equal to summation theta curl summation yi minus beta naught minus beta 1 xi whole square, right? So how do we minimize it? So what we have, theta curl is equal to beta 1, right? So how do we minimize it? We just do del b naught, sorry, del l d beta naught is equal to 0, and we do dl d beta 1 is equal to 0. From this dl d beta naught, we get following. If you just do beta naught with respect to square it, you get minus 2 summation of 1 to n yi minus beta naught minus beta 1 x, so like twice comes in here, gives to minus 1 is equal to 0. And in this case, we get minus 2 summation I from 1 to n. There's an xi minus twice x minus xi for this beta naught beta 1 xi into yi minus beta naught minus beta 1 xi is equal to 0. So these are called normal equations. Okay, so these are essentially called normal equations in the sense that they normally arise from this. I don't know why it's called normal equations, but yeah, so these are the two equations which are called normal equations. That's important. Very good. So now, based on these two equations, essentially we need to estimate what? We need to estimate this beta naught and beta 1. Okay, and what we got, this xi and yi's are given data, so they're constant. So we have got two linear equations. What are the linear equations? Summation of 1 to n yi minus beta naught minus beta 1 xi is equal to 0. So if we get from here that if you just do, so I will try to do it in terms of y bar 1 by n, because that makes much more statistical sense, minus beta naught minus beta 1 x bar equal to 0. And from this, what we got summation of 1 to n is 2 and 0 cancels. Okay, xi yi minus, we have this beta naught with corresponding xi's. Okay, so we get minus summation, there is a 1 by n over here before this summation. So essentially what I'm writing this down soon, but essentially what we got out of here, that we got two linear equations in beta naught and beta 1. I don't know, my computer hanged a bit. Just wait for a minute. Yeah, it came back alive. There's 1 by n over here minus beta naught x bar. Okay, we are dividing 1 by n over this minus beta 1. What do we have? Xi square. Summation 1 by n xi square is equal to 0. So therefore we got these two linear equations. This one, oops, this one and this one. They look ugly in terms of corresponding algebraic form, but we need to solve this. Okay, now I will not solve this in class. It's like really so you can solve this out. Essentially what we'll get is the following. Let me write down the equation. So you will get that y bar is equal to beta naught plus beta 1 x bar. Sort of the mean of the y's is predicted by this corresponding linear equation that we have got. So essentially what we get the beta naught hat. Okay, this is the estimates. And another thing we get is there, that's if you solve the beta 1 hat, you will get that it's sxy by sxx. So what is this? This is summation of, so sxy, let me write sxy, summation 1 by n, summation of xi, let me not write out here. So it is very important. So we will tell about this more, about the beauty of this. But essentially it means the following. It means that if you write out like this, summation xi is sort of the base of any two equations, a comma b is summation of ai minus a bar times bi minus b bar. Okay, and what we get therefore sxy is equal to summation of xi minus x bar times yi minus y bar, and therefore sxx is actually sort of the variance of the, not the variance but yeah, whole square. So this is the two format we will get. Okay, and remember this one, and from here you got the two beta 1 hat, and from here you will get the beta naught hat. Okay, so you will get the following. You will get that beta 1 hat you got as sxx by sxy by sxx, and beta naught hat, what was that? It's y bar minus beta 1 hat x bar. So it's sort of y bar minus sxy by sxx x bar. So these are the two equations you got. Okay, and this is very important. Now what we will do next, in the next part of the video, we will try to see the various beautiful things coming out of this normal equations. Okay, very important stuff, and we will do it and related to some geometrical stuff, linear algebraic stuff. Okay, we will see that how s x comma y is related to the covariance. Okay, sorry, it's related to the covariance, it's related to the inner product. What is inner product? Dot product of two vectors. Okay, we will see this. So see you in the next video with this beautiful mathematical geometric stuff. Bye bye.